right, when we're looking at something like this, what are we going to start with?
The base.
Mm-hmm. Yep, our base 2. What are we going to do with that 2?
Do the x and y.
Yeah, we're going to take that base of 2 and put it as the base of our exponential that we use to build our logarithm. So we're going to take base of 2 and use that to build the table for 2 to the x with our x's and our y's. I have very limited space, so I'm just going to use that spot right there for my exponential. And that's when we pick our x values, -2, -1, 0, 1, and 2. And that gives us our y values of our 1/4, Is he eating through the pencils? I was gonna say some of them. That just means that one got flexed in shipping, and the lead is snapped all the way down. There we go. That one's got a point. Yeah, sometimes the cheap pencils, especially when they start getting worn down, they won't hold it. So we're not going to graph that table. 2 to the x, good information to have, really helpful. We're going to need it to make our parent function for our logarithm, but we're not graphing those points. The pieces we need to be able to graph are when we swap it and get our log base 2 of x. And we get this from the fact that exponential functions and logarithms are inverses. So what was the y becomes our x, and what was the x becomes our y. So we literally just flip our 2 columns to get our 1/4 with our -2, our 1/2 with our -1, our 1 with our 0, 2 with 1, and 4 with 2. This one we're going to graph. And on this one, we can also see our asymptote, because on our exponential functions, we had asymptotes at y equals 0. So on our inverse over here, on our logarithm, we have an asymptote where x equals 0. Because everything that was an x became a y. On our parent functions, we typically do not graph the asymptote simply because it makes your page way too busy, and it is the y-axis anyway, so it's not humongously detrimental if we don't. But when we plot up our points on our parent function, it looks kind of like this. This is our f of x. That is our parent. We use this to build our transformations. We're going to get our transformations from applying our a, h, and k. So we're going to take our x's to add the h. We're going to take our y times a plus k, because graphing makes us yak. So if we're taking our x's from our parent function and adding h, what is our h? Super close. +3. So our h is going to be that +3, which means which direction do we expect this to move? To the right. What's our a? It's not the 2. The 2 is our b. That's our base. A is multiplied out in front. Nothing. There's nothing written there. It's an invisible 1. Since it's multiplied and nothing's happening there, it's a 1. Because 1 times anything is the same thing. You don't have to put the 1. I just like us to make sure we notice all the pieces. And then our last piece is our k. What do we see there? what way is that going to make it move? Up 2. So we're taking our x's and our y's from our parent function and applying these transformations. So we're taking all of our x's plus 3. So my 1/4 plus 3 gives me 3 1/4, or 3.25, depending on how you like to go. 3 1/2, or 1/2 plus 3 gives us 3 1/2, or 3.5 if you're a decimals fan. 0 plus, or nope, sorry, 1 plus 3 gives us 4. 2 plus 3 gives us 5, and 4 plus 3 gives us 7. Our y's, same vibe. -2 times 1 is -2, and then plus 2 gives us 0. -1 plus 2 gives us a 1. 0 plus 2 gives us 2, and then a 3, and then a 4. Before I plot these points, we also need to do our asymptote, where I'm going to take my x equals 0, and we can use our transformation over here. 0 plus 3, our asymptote's going to happen at x equals 3. Since it's on an x, it goes through the x transformation. So it's going to make it scooch to the right. So I am going to graph my asymptote for our transformed function here. So at 3, my asymptote's over here. I don't know why these are all starting to look like commas. There we go. Better? Kind of. I don't know. Still comma E. But we got to graph that asymptote. That's our wall that we cannot Kool-Aid man crash our way through. Oh, yeah. Now we can plot up our points. My 3/4 0 gives us a point here. 3 1/2, 1, we get a point here. 4, 2, 5, 3. I was directly behind my word, but that's okay. And 7, 4, which you guys are slightly closer to being able to plot, but it's still going to be off your graph. Mine's a smidge smaller, but that's okay. It's just going to mean that my picture looks a little bit more crowded than yours does. A little bit more cramped. But it's still the vibe. So this is our transformed function. This guy is our g of x. I'm just going to relabel my f of x down here just so things are separated. Whoa, chonky pen. F of x. So our last two pieces here, because we already described our transformations, what is our domain of g of x?
3 to infinity.
From 3 to infinity, every single time. And our range?
-infinity.
Gorgeous. Negative infinity to positive infinity. Every single time. That range is going to be negative infinity to positive infinity. And our domain is always going to have our h in it. So it's going to be h to infinity. We're not going to see it reflected the other way where it's negative infinity to h. That's more of a pre-cal thing. So if you do pre-cal, you'll see that. But we're not doing that reflection for us. Okay. Questions on this graph? Okay. It's our last graph of the day. We're not going to keep graphing today. Yay! We are going to be in our notes packet, though, so you're going to go to page 6 in your note packet. And we're going to do some writing. So, page 6 in the notes packet. All of this stuff is the very top line on that page. I just wanted to have a little bit more space so it was bigger so y'all could see it. So it says things to remember at the top. Our exponential form versus logarithmic form, and then there's a very long blank. That's things we've worked with already, things we've seen before. Our exponential form, that's the B, P equals A, our BPA. And we can switch that, switching back and forth with our log base b of a equals p. We're not going to do a ton with switching forms today, but we're going to do a lot of stuff with logs. And so remembering what they are and what they mean is an important piece. We've got a couple of special situations here now that we've worked with logs a little bit that we're going to write down. Honestly, it's mostly because there's not another great place to put these, but they're good things to notice and good things to see. And we kind of worked with these a little bit when we were evaluating 2 days ago. But I want us to think about these. Log base b of 1. So if I have any base with an argument of 1, so if this guy's 1, meaning this guy's 1, what power does a base need to have for this to be 1? 0. Because anything raised to a 0 power is 1. So any log, no matter what the base is, if the argument is 1, has a power of 0 every time. What if our argument equals the base? It's the same thing. Like log base 2 of 2. So my base is 2, my argument's 2. So that would be 2 to the something equals 2. You're exactly right, Daniel. It's that it would be a 1. So just so you can see that if that was like log base 2 of 2, I could write that as 2 to what power equals 2? That's what we're saying here, 2 to the first. So again, these two aren't going to come up super much. Like today, we're going to use them, I think, on Tuesday. But I didn't want us to be like introducing that and be like, oh yeah, I remember this too. So that's everything in that kind of top line. Then we're going to fill in those 3 properties. I'm going to give you guys a second to write this down because I see a couple people still writing. Those next 3 lines, the properties of our logarithms, that is like our main thing we're going to focus on in this section. 8.2 deals with these 3 properties a bunch. And today what we're going to work on is we're going to do something called expanding using them. So I'm going to give us our properties. We're going to get some steps to work with. I'll tell you why. And we'll do this. So properties of the logarithms, we have 3 of them. We've got a product property, a quotient property, and a power property. So our product property, what this is looking at is this is saying if I have 2 things being multiplied in the argument. So if we have log base b, any base, of 2 things being multiplied, m times n. Our product property tells us that I can rewrite this as log base b of m plus log base b of n. So our multiplication can become addition. Get rid of this. So our quotient property is very, very similar. It's just saying now instead of having a product in my argument, if I have a quotient in my argument, quotient meaning fraction, division. So our quotient property has log base b of division, m over n. We can rewrite this as log, with that again keeping the same base, log base b of m minus log base b of n. So we can take division and turn it into subtraction. And the last one is called our power property, which if our product was things being multiplied in the argument and our quotient was things being divided in our argument. Our power property is things that have powers in the argument. So our power property is going to look like log base b of m to the power of n. We can rewrite as n, wrong color, n log base b of m. So our powers come down and become coefficients. They become the number in front. So these three properties are going to be really what we use over and over and over again today and on Monday. We're going to use these bunches and bunches and bunches. Because what we're going to do is we're going to take logarithms that have gobbledygook after them, and we are going to play with them like they're made of Play-Doh, and like take a ball logarithm and we're going to roll it out and make it into a really long snake. And at some point I'm going to give you a really long one, and we're going to take it, we're going to crunch it up and put it back into a little single log. Because when we are trying to evaluate logs and calculate logs and figure out what they equal to a number, doing logs and their calculations when they're not pretty powers are super gross. And before we had calculators that could do logs very, very well, you literally had to look it up in a book. So log base 2 would be in a book. You'd have to flip back to your log table, and you'd have to look them up because you couldn't type them in a calculator that didn't have all those buttons. So we're going to be working with them and kind of expanding them around and moving them around, because until very, very recently, we didn't have calculators that could do a logarithm. Like, that was not a thing that existed 20 years ago. They couldn't do it. So we have these 4 reasons. I promise it'll make things easier when we're solving, but it's going to feel very, very weird. So since we're doing a thing and it's going to feel weird, I'm going to give us steps. That's what our next 3 spots are. It says steps to expand. And I know you guys do not have this big yellow box, but I thought it was a very helpful piece to put out. So our steps, these are not math law, but these are what we have found as ways that give 99% success for most people. Is we're going to take our very first step should be to work with our quotient property. So when we are trying to make things spread out and make them bigger, we're going to take division, and this will be the first thing we change, will become subtraction. So our first step when we are trying to expand something is any place we see division, we're going to turn it into subtraction. So division becomes subtraction. Our second step will be to work with the product property. So any place we have multiplication, it's going to become addition. Write it down here. And then once we've done our quotient property and our product property, then we'll deal with our power property. So our powers, or our exponents, they will become coefficients, is the technical term for it. If coefficients is not a familiar enough word for it, you can put multipliers. That also means the same thing. It's going to come down and be the number in front. So sometimes when we're looking at these and we're trying to make things and stretch them as far as we can and expand it out until we're going and going and going, it's hard to know when to stop. So we know we are done, which I just kind of put this off to the side and I just wrote goal or something like that. You know you are done when each log has only one term in the argument. So like log base 2 of x has one term in the argument, just the x. Log base 3 of x squared does not have one thing in the argument. That still has two pieces, x squared. ln of 4 has one thing in the argument. ln of 4x has two things in the argument. So it would have more steps to do. So these are what we're doing, and we are going to do at least 1, 2, and 3. We may or may not get to 4 just because I want to make sure we take our time looking at these examples down here at the bottom. But we are definitely doing at least 1, 2, and 3. Okay, so these are the steps we use. This is a kind of checklist. So we start with finding division and making it turn into subtraction. So every time we expand it out and we do one of these properties, we're going to put more logs. So it's going to have the word log a bunch of times. Because if we look back at our properties, I'm going to switch for a second. I took my one log and made 2 of them here. So we're going to expand these out. It's going to have more word logs. I'm going to write the word log a bunch of times. So let's look at these. So here's number 1 down at the bottom. It says expand the expression. So we're going to use our little steps above there as a checklist. So my first thing we're going to do is we're going to do division becomes subtraction. I do have some division here. We have this little fraction bar. That guy's division. Division is going to become subtraction. A fraction bar kind of looks like a minus sign. Our division becomes subtraction. So what we're going to do to expand this out, this is the common log, so it has a base of 10. We don't have to write it. So we can just write this as log of our numerator, that 5y. Our division becomes subtraction, and we're subtracting our denominator. So we write our log again, log of x to the 4th. We should write log more times every time we do our product property or our quotient property. We're going to write log more often.
Log.
Mm-hmm.
That is going to get stuck in my head, and I should be tired but I'm just scared.
Oh, yeah. Yeah. You will. That's okay. So here we've done our division that became subtraction. We made it out into 2 separate pieces. Numerator minus denominator. Our next step is to do our multiplication becomes addition. We do have multiplication in here because we have 5 times y. Every place we have multiplication, it's going to become addition. That's our next property we're going to work with. So I'm going to take my log of 5y and put that through my product property. Again, my base is going to stay the same, so this is going to become log of 5 plus log of y minus log of x to the 4th. Nothing over here changed. I'm just bringing them down. So this is using our product property. Our last piece is to use our power property. Any exponents we have are going to come down and be coefficients. So my 4 is going to come down and be in front of that particular piece. So I'm going to rewrite the whole thing. I'm going to write log a bunch of times today. Log of 5 is just coming straight down. Our log of y is coming straight down. We have our minus. Our power comes down and becomes a coefficient. So instead of having a power of 4, we're going to have 4 times log of x. So we've used all 3 of our properties, but the way we check and see if we're done is we make sure that each log has one single term as its argument. If each log has one single term as its argument, then we are done. And this is our fully expanded answer.
That's the answer.
when we have one single term on each log, it's done. These will get wide. They're not long problems, but they are wide problems sometimes. They will have, I think, at most 3 or 4 lines. Okay. So now we have written all the properties once, and we have used all the properties once. Questions on that first one? We will see all the properties at least one more time, but not necessarily on every problem. Okay. So let's look at this next one, number 2. Again, we're going to work with our properties, but this time we get to skip one. Because for number 2, we don't actually have any division. So division becomes subtraction, done. There's no division. So we're going to go straight to doing our multiplication that becomes addition. We just have a bunch of it. Because I have 4 times x squared times y to the 8th times z. Every place we have multiplication, it's gonna become addition. Every single time. Every time we switch our multiplication to addition, I'm gonna write my log base 3 again. So this one's gonna get real, real wide. Because we're gonna have our log base 3 of our first piece is 4. And then we have a multiplication. Multiplication becomes addition. And I have to rewrite the log. So log base 3 of x squared. I have another set of multiplication, so we're going to switch that to addition, which means I need to re-put the log. Log base 3 of y to the 8th. And again, we have another multiplication here, plus log base 3 of z. Told you, wide. They don't get long, but they get wide. Every place we have things that are multiplied together, which means things that are pressed together, I need to switch my multiplication out to be addition. Questions on that one or that step?
What was the second one? I know the
Mhm.
4 became addition.
Mhm.
What was the second?
So 4 times x squared, so we had to split those guys up. X squared times y to the 8th, so we had to split those guys up. Y to the 8th times z, we had to split those guys up. So they're all pressed together, so they're all being multiplied together. So we can do them all in one go like this. So every time they're pressed together, we're going to break them up. We've got to separate them. They're like you have a bunch of little siblings in the back seat. You're like, no, separate. You're going to put a little place between you. Get some space. We're about to do that next. That one's not done yet. Okay, that was just first step. Because, yeah, our next step is to go, well, I still got those powers. We need to use our power property. So I've got a power of 2 that needs to come down and be a coefficient. And I have a power of 8 that needs to come down and be a coefficient. Those 2 pieces are our next things to deal with, using our power property. So our log base 3 of 4 isn't going to change. He's still chilling. Log base 3 of 4. On our log base 3 of x squared, that 2 is going to come down and be a coefficient. So we're going to have 2 log base 3 of x. And then we're going to have our plus that still hangs out. I'm going to make that be the same size as the other one. Our 8 also needs to come down. It's going to become a coefficient. We're going to have 8 log base 3 of y. And then our log base 3 of z is just chilling. Log base 3 of z. And then to see if we're done, the way we can check is we look and see if each log has only one thing in its argument. So log base 3 of 4, that's one thing. 2 log base 3 of x, x is just one thing. Log base 3 of y, that's just one thing. Log base 3 of z, that's just one thing. That's what we're looking for. When we are done, there's just one thing. No powers, no fractions, no nothing else. So this is our fully expanded logarithm. These get wide. Okay. Questions on this one? We're gonna do, let's do number 3 for sure, and then we'll see what we're looking at time-wise for number 4. So let's look at number 3. We've got ln, that's log base e. So that's just log base e. We can keep it as ln. You do not have to write it as log base e. Just makes things easier. So we've got ln of this 3wx squared over y to the 4th. So we are going to use all 3 of our properties on this one. First thing we need to do, very first step, division is going to become subtraction. Fraction bars kind of look like minus signs anyway, because a fraction bar is just a blank fraction. Oh snap, what? So division becomes subtraction. The fraction bar helps us kind of remember that it looks like a minus sign. So we can rewrite this as ln, our natural log, which I always write kind of cursively, just otherwise it looks like the word in, because my handwriting's weird. So we have our numerator, 3wx squared, and then we need to subtract our denominator. But we also need to make sure it stays as a log. We're subtracting ln of y to the 4th. We do not just subtract the y to the 4th. Every time you switch to a new operation there, you have to rewrite the log. The most common mistake I see is that we just expand this part and we don't rewrite log more times. We're looking to write log as many times as we can in each of these. I want so many logs. We're gathering firewood. As many logs as we can. So division becomes subtraction is our first step. Then we're going to do multiplication becomes addition. Well, I don't have any multiplication over here, but I do in here. We have 3 times w times x squared. So every place we have multiplication, we're going to make that become addition. Every single place we have it. So when we rewrite this, expanding it out, we're going to have our ln of 3 plus, now I need a new log, so we're going to have ln of w. Again, I've got multiplication, so I'm going to switch multiplication to addition. Since I have a new plus, I need a new log, ln of x squared. We're finally out of that string of multiplication, and we need to subtract our ln of y to the 4th. So this one, the green step here is using our quotient property. This pink step here is using our product property. Our last step is to use our power property. So I don't have any powers on my ln of 3. I don't have any powers on my ln of w. I do have a power here. So we need to take my squared from my x squared and bring that down as a coefficient. And I need to take my 4 from my ln y to the 4th and bring that down as a coefficient. So our last step on this one, we're going to have our ln of 3 plus our ln of w plus 2 ln of x minus 4 ln of y. And again, we can check and see if we're all the way done by seeing if there's any logs that have more than one thing in the argument. So we have ln of 3, ln of w, 2 ln of x, 4 ln y. There is only one thing after each log, which means these are our answer. This, one single thing. That's our answer. That's fully expanded out. Okay. We have 5 minutes, and I'd rather us have time to look at homework 1 if you guys have any questions on anything like that. Then try and sprint through number 4. Number 4 is a great one to do. It does expand out very same way, same properties, but I want to give us a chance to look through stuff and ask questions if we have to. We have done everything on 8-1, so we have all that answers, which means there's no expanding on homework 1, which means I'm going to give you homework 2. Again, just look at it. Okay, so I'm going to pass out homework 2. Homework 2 is going to be due on Tuesday. We are going to do the opposite direction of this on Monday. So we're going to take really, really long ones, and we're going to smush them back into a single log. It's called condensing. So we can do all of the expanding stuff, which is actually on the back. And the front side has our condensing. Okay? So, I have reminders up here. Please turn in your homework 8-1. Turn in your bell work for week 11. Please make sure your name is on it and the fact that it is week 11. That makes things, honestly, manageable for me. Otherwise, it is a pain in the teacher.
I accidentally did it on the wrong one.
On the wrong day?
The wrong week.
Oh, out an old one?
Yeah, I was looking from the back.
It happens. It happens. Just, I would say you can just like make a note of it on whichever one it is. Alright, so there's homework 2.